one of the most exciting applications of Boltzmann machines, especially Restricted Boltzmann Machines, RBMs, and Deep Belief Networks, DBNs, has been in image recognition. These models excel at learning deep structured representations from visual data, making them valuable for tasks like feature extraction, object classification, and facial recognition. Before convolutional neural networks, CNNs, became the dominant approach, Boltzmann-based models played a crucial role in pushing the boundaries of machine learning in vision tasks. The key reason Boltzmann machines work well in image recognition is their ability to learn hierarchical features. Instead of relying on handcrafted image features such as edges, textures, or shapes, these models automatically discover patterns by adjusting the weights of their connections. The hidden layers in an RBM or DBN act as feature detectors, capturing increasingly complex representations of an image. Early layers learn simple patterns like edges and corners, while deeper layers capture more abstract features like object parts and structures. In a typical image classification pipeline, an RBM can be used as a pre-training step, learning important visual features from raw images. The learned features can then be fed into a classifier, such as a support vector machine, SVM, or a fully connected neural network to perform final predictions. This approach was particularly useful in the early days of deep learning, helping models achieve better accuracy on tasks like handwritten digit recognition, MNIST, and object detection before CNNs took over. In a typical image classification pipeline, an RBM can be used as a pre-training step, learning important visual features from raw images. The learned features can then be fed into a classifier, such as a support vector machine, SVM, or a fully connected neural network to perform final predictions. This approach was particularly useful in the early days of deep learning, helping models achieve better accuracy on tasks like handwritten digit recognition, MNIST, and object detection before CNNs took over. Another important application of Boltzmann machines in vision is feature extraction for dimensionality reduction. Instead of using techniques like principal component analysis, PCA, an RBM can learn low-dimensional representations of high-resolution images, preserving the most important features while reducing computational complexity. This is useful in cases where storage and processing power are limited, such as mobile devices or embedded systems. Boltzmann-based models have also been explored in facial recognition, where they can learn identity-specific features from training images and then compare new faces against known identities. Although CNN-based architectures like FaceNet and VGGFace have surpassed them in performance, RBMs and DBNs laid the groundwork for modern deep learning-based face recognition systems. Despite their contributions to image recognition, Boltzmann machines have largely been replaced by CNNs, transformers, and deep autoencoders, which offer better scalability and computational efficiency. However, research into hybrid models, combining energy-based learning with convolutional layers, is still ongoing, showing potential for future advancements in AI-powered vision systems. Now that we've seen how Boltzmann machines have been applied to images, let's shift our focus to another fascinating area, natural language processing, NLP. While not as common as transformers today, Boltzmann-based models have been explored for text generation, language modeling, and machine translation. Let's dive into their impact on NLP next. Boltzmann machines, particularly restricted Boltzmann machines, RBMs, and deep belief networks, DBNs, have also been explored in natural language processing, NLP, a field where understanding complex relationships between words and context is crucial. While modern NLP is dominated by transformer-based architectures like GPT and BERT, Boltzmann-based models played an important role in early deep learning approaches to text generation, language modeling, and word embeddings. One of the key strengths of Boltzmann machines in NLP is their ability to learn probabilistic representations of text data. Unlike traditional rule-based systems, they don't just memorize word sequences. Instead, They learn the underlying statistical structure of a language. This allows them to generate coherent and contextually relevant text, making them useful in applications like automated content creation, text completion, and conversational AI. A major application of RBMs in NLP has been in word embeddings, where words are represented as vectors in a continuous space based on their relationships with other words. Similar to how Word2Vec and Glove learn embeddings from large text corpora, RBMs have been used to capture semantic meaning and syntactic relationships between words. This approach helps improve machine translation, sentiment analysis, and information retrieval by representing words in a way that reflects their real-world usage. Boltzmann machines have also been used in language modeling, where they predict the likelihood of a given word sequence. By training on large datasets, they can learn to generate text that mimics human writing, making them useful for tasks like AI-generated poetry, dialogue systems, and text summarization. However, because training Boltzmann-based models is computationally expensive, they have largely been replaced by recurrent neural networks, RNNs, long short-term memory networks, LSTMs, and transformers, which scale better and learn faster. Despite being overshadowed by newer architectures, the unsupervised learning capabilities of Boltzmann machines still make them valuable in some NLP applications, especially where labeled data is scarce. In areas like topic modeling and document clustering, they can uncover hidden structures in texts, making them useful for automatic categorization of news articles, research papers, and customer reviews. While they may not be the leading choice for NLP today, the principles behind Boltzmann machines, energy-based learning, and probabilistic reasoning continue to influence advancements in AI-driven text generation. Some researchers are exploring hybrid models that combine Boltzmann machines with deep learning techniques to improve efficiency and scalability in NLP tasks. Now that we've seen their role in NLP, let's move on to another critical application: recommendation systems. Here, Boltzmann machines have been used to predict user preferences, improve content personalization, and enhance online shopping and streaming platforms. Let's explore how they have shaped this space next. Boltzmann machines have played a significant role in recommendation systems, helping platforms like Netflix, Amazon, and Spotify predict user preferences and personalize content. While deep learning has taken over much of the recommendation space, Boltzmann-based models, particularly restricted Boltzmann machines, RBMs, were among the first successful neural network approaches used for collaborative filtering and content suggestion. At the core of any recommendation system is the ability to predict what a user will like based on their past interactions. Traditional methods like matrix factorization, e.g., singular value decomposition, SVD, focus on finding relationships between users and items, but they often struggle with sparse data sets where users have only rated a few items. This is where RBMs prove to be highly effective. They could uncover latent patterns in user behavior by learning probabilistic relationships between users and the products, movies, or songs they engaged with. In an RBM-based recommendation system, the visible layer represents user-item interactions, such as movie ratings, and the hidden layer learns deeper representations of user preferences. By training the model on existing user data, it can infer missing ratings and predict which items a user is likely to enjoy. Unlike traditional collaborative filtering methods, RBMs can capture nonlinear relationships between users and items, improving the quality of recommendations. One of the key advantages of using RBMs in recommendation systems is their ability to handle sparse data efficiently. In many real-world scenarios, users only interact with a small fraction of the available items, making it difficult for traditional models to generalize. RBMs mitigate this by learning meaningful features from limited interactions, making them particularly useful for personalized content recommendations in e-commerce, video streaming, and music platforms. Boltzmann-based models have also been explored for personalized recommendations beyond user ratings. By incorporating additional information such as browsing history, purchase behavior, and contextual data, these models can refine predictions and provide more accurate, tailored suggestions. This approach has been used in fields like news recommendation, online learning platforms, and targeted advertising. Despite their strengths, RBMs and other Boltzmann-based models have been largely replaced by deep learning techniques like neural collaborative filtering (NCF), autoencoders, and graph-based recommendation algorithms. These newer models scale better with large datasets and benefit from advancements in GPU acceleration, making them more practical for modern large-scale recommendation systems. However, the legacy of Boltzmann machines in recommendation systems remains. They were one of the first neural network-driven approaches to personalization, influencing the development of more advanced deep learning-based recommendation algorithms. Some researchers are even revisiting hybrid models that combine RBMs with deep neural networks to improve accuracy and efficiency in personalized content delivery. With their impact on recommendation systems explored, let's look at where Boltzmann machines are heading in the future. Are they a fading part of AI history, or could they make a comeback with new advancements in technology? Let's explore what's next in the world of Boltzmann machines.